with light sheet, something that you want is to be able to control the dimension of your beam. The reason is that, I don't know if you remember, but I mentioned the fact that it is important to control the thickness of the light sheet, because if you have a light sheet that is thick, then you will excite the fluorescence from a thick layer. So you don't have a good axial resolution. If I can, but if the light sheet is thick, you have a long Rayleigh length, which means that your light sheet will be homogeneous in space. So it depends. Sometimes you want a very thin light sheet and a very short Rayleigh length because maybe your sample is small. Other times you prefer to have a wider, a longer, let's say, light sheet and a thicker one. But to be able to change that, what can we do? Well, we can start with either a large, very large beam, and indeed that will give us more focusing effect, or we can have a smaller light sheet and then the focusing of this beam, a smaller beam, and then the focusing, the capability of a lens of focusing it will be reduced. So we will have a thicker light sheet and a longer one. So I want to expand the beam. That's what I want to do. So that I have, then I can play with it and I can make it smaller or leave it untouched, depending on what I want to do. How do I do that? Here I have the first lens that is, this is a 53 millimeters length, 53 millimeter focal length lens. So what does it do? It focuses the beam in one dot, okay? In one very small dot. This is the focal plane, more or less. It's here. Can you see that it's focusing? Okay, so this is what a lens does. And then after the focus, it becomes larger again. Okay? It becomes larger and larger and larger, and it is divergent. If I place the second lens at a distance from the focus of the first lens that is equal to its focal length, which means the distance between the two lenses is equal to the sum of their focal lengths. Okay, what happens? It happens that after the two lenses, my beam is collimated again, and it is expanded 9 millimeters.
Yeah.
Right? Let's see. I'll try to stay still. It's 9 millimeters.
Yes.
Okay. So it's 4.5 more or less, a little bit less maybe. Okay. So there is nothing much very really special. I won't have shown to you now, but I want to mention the fact that here at the focal plane, in between the two lenses, at the focal plane from this lens, we have a Fourier plane. The focal plane is a Fourier plane. If I wanted to do some spatial filtering, I would do it here. Can I do something here? Yes, I could. For example, let's see if it is still well aligned. Elvis aligned it. Let's see if it is still. Can you? Well, maybe you can see it from here. But if you come a little bit closer and you look from here, there is the central spot and all the others as well. Okay, so this is a DARE beam, the one that we've been talking about. And I would like to select, for example, if I want to select only the central spot, I can put here another pinhole that will reject all the other frequencies, all the ones that are around, all those rings, for example. After this, I have something that is quite nice. I think some of you might have already seen it because I've shown this the other day. Anyway, so this is a cylindrical lens. It is a lens that has, it's basically like a cylinder that was cut. It has, it's not spherical. You can already imagine if it has a curvature that is only in one direction, it will focus only in one direction. So if this focuses only in one direction, we can create a blade of light, right? So I can show you. I will put it here in front of in the middle of my beam. Of course, we have been aligning this system quite a lot. I will touch it here. So, and to align the system, we have positioned the pinholes. When you want to align a system, what you want to do is basically make sure that your laser is passing through pinholes or irises actually. And to align two irises, you usually use two mirrors, or you need to have 2 degrees of freedom. In this case, we align the system with this mirror and this mounting that can tilt the beam, basically. Okay. I'm going to remove the objective because I want you to see a little bit better. Okay, so the idea is that this lens, now we don't care about what is in the middle. This lens is a lens that creates in its focus a line, okay? We saw here a spot. For the cylindrical lens, the focal plane, at the focal plane we should see a line. Now the focal plane of this lens is actually on this mirror right now. And maybe I will just show you. Let's do like this so it's more clear. If I put it here, okay, at its focal length, which is in this case 50 millimeters, I should see a line. Okay, so here we have a line. Is that if I move this piece of paper very quickly, you should be able to see a vertical line or a vertical light sheet. Can you see that? Okay, I don't know if you can see that, but I'll show you what happens if I rotate it now. So if I rotate it, I will have an horizontal line. If I'm managing to, sorry, I will just move this. Let me see. And if I move it from the side, you should see that it is like a standard beam, and from the top, we should see a plane. There is another way of visualizing this. So here in this cuvette, I have just put some highlighter. That's it. I just put I just put the tip of this highlighter in the water, and you can see. So 532 is green. So you see green because the laser is green, but you should also see yellow, okay, or orange. So I put something that is fluorescent in the orange. In fact, it is this one. So, okay. If we want to see better what happens there, we could use a filter, okay? So the filter is something that basically cuts some of the wavelengths that we are not interested in. For example, the laser. I don't care about the laser. I want to see the fluorescence. So I want to reject the green light, and I want to be able to see only the yellow or orange light. So this filter is a dielectric filter. So it doesn't work in absorption, but works in reflection. Okay. So it will reflect, in this case, everything that is below 550 nanometers, while it will let all the other wavelengths pass through. Okay. So I will use this in my detection line to get rid of the laser. But the nice thing is that if I look through it, I can see the fluorescence here. Can you try to? So first of all, don't break it. If you look at the outside, okay. If you look at okay, you can see what color.
It's orange yellowish.
Okay. So can you tilt it now? Can I hold it for you? You look through. Okay, now if I touch it like this, do you see still the same color?
No.
Okay, so that's something important. Dielectric mirrors or dielectric filters, they work in reflection, and they are angle specific. They work well only at a specific angle. In this case, the orthogonal, the incidence must be orthogonal. If you arrive at an angle, it's not good. You will filter different wavelengths. So now, if you hold it again, and you go there, tell me if you see any green.
No, there's no green.
Okay, but you see what color? You see the fluorescence?
Yeah.
Yes, perfect. So it works. Anybody else wants to it's just a green. It's
yes, not current.
It's nothing that special, but I want you to realize that with that filter we are going to cut the green, correct? So you don't see green. Okay. Can you see? Do you see clear? Look through. Nothing. So you just look through. If you look through, you should see that this solution
There is no green.
Okay, great, perfect. So that you see the orange,
Yes.
but you don't see the green. There, if I put the cylindrical lens, let's see in the cuvette what happens. So, first of all, so now you, sorry, no, 1 second. Okay, first of all, before looking at the cuvette, I would like to ask you, so let's put it like this. This lens has a focus here on this mirror that is then recollected by another lens, this one. This lens is 50 millimeters length, and this lens then has its own focus that is projected here, and it's taken again by another lens. These two lenses are the same focal length, okay? So they do nothing to the dimension of the beam. So let's pretend that this cylindrical lens is here. Okay, let's pretend that. Again, an image plane, no, sorry, the focal plane of the lens is here or now, and it's vertical. Okay, if I rotate the cylindrical lens, I can rotate it. So now it's horizontal. Okay? But when I look in far field, over there, it's vertical. Horizontal and there vertical. How the different lenses and different optics behave in the close field and in the far field. All right. Now, the thing is, I could have put this lens just here and illuminate a blade of light, a blade of sample, and collect the fluorescence with my detection line. But I decided not to do that. The reason is that this lens will create a waste that is very small, and it has to be matched with the field of view of this objective. It's not very easy to do. I need something that allows me to be very precise. The other thing is that I need the position of the light sheet to be matched with the focal plane of this objective for the detection. And that's the focal plane has a depth of field of few micrometers. Let's say maybe if we are lucky, 50 micrometers. It's a very small, you know, I have to be precise in positioning my plane of light. And then the other thing is my beam could be tilted. Okay, so if it is tilted like this, I won't see an image that is focused because the focal plane is flat. And if I arrive with a light sheet that is tilted, it's a mess. So, okay, how do we do that? How do we solve the problem? Well, we need something that allows us to be precise. Okay, so if I rotate this mirror, what I'm going to do is basically be able to translate it thanks to the fact that this mirror, this lens converts the angular displacement into a lateral displacement. Okay, so by rotating very slightly this mirror, I can translate the beam. Okay, cool. Now, that's with one lens, but I also need to have a degree of freedom for the tilt. So I've put here another mirror in the focal plane of this other lens. So let's think about it. So that's how I'm going to basically be able to move my light sheet in the three-dimensional space. We have to keep in mind that after these two, then if I use a lens like this one, a 50 millimeters focal length lens, the thickness of the light sheet, which will be, let's say, which will be determined by what? By the dimension of the beam, of the incoming beam, and also by the focal power of this lens, will be of few tenths of micrometers. I want a light sheet that is thinner than that because I want to be able to section precisely my sample. So I put another lens that will be an objective. Okay? So I will put this guy. So this is a 5x objective with a 0.14 numerical aperture. So again, a numerical aperture that is not the best for this type of objectives, but allows me to have a long working distance. Okay, so let's see what we observe. Okay, first of all, now we have a very thin light sheet in the cuvette. Okay, so if you look in the cuvette now, you should be able to see clearly that there is a light sheet that now is horizontal. Now, if I rotate it, now the light sheet is vertical and there is horizontal. Okay, and that's pretty cool in my opinion. Okay, do you guys see it? Can you see it? Tell me if you see it or not, because otherwise I've seen it many times. So I don't need to, but I want you to see it. Can you see it?
Yeah.
Okay. Okay? Oh. Yes, please come closer because, okay, so this is now horizontal. And this is, okay. Can you see where it is? Okay, so you can tell that there is a minimum thickness, right? Okay. It's maybe not super obvious, but if you look, can you see? Okay, so if I rotate, so imagine I'm looking at a sample that is like, who was saying that? Somebody said that we are just bags of water. I don't remember, walking bags of water. And so imagine if I have a bag of water here and I want to look at it in 3D. And so I'm moving it through the light sheet. What happens is that the light will encounter different thicknesses of this bag of water. And this means that it will be, let's say, refracted in many directions. And it will never be the same at different positions. But if I start with a cuvette full of water and then I put my bag of water inside and I move it, the index of refraction, the overall index of refraction, the overall optical path that the light will experience will always be the same, because I'm matching the index of refraction of everything that is inside here. So I put this because I know a priori that I'm going to put something in there that is full of water. Okay, so let's say that I've done things properly, and indeed we can switch off the light and say, okay, so I put here my light sheet, and now I have to look at something. So I want to look through the camera. Okay, the first thing, you can come. So the first thing I want to do, so I think that everybody should go that way, so that you can see on the camera. So I'm changing the exposure time. I'm changing the exposure time because it was too bright. So it was not, if your image is overexposed, you cannot do anything with it, because if everything is white, I mean, how can you quantify anything? You cannot say this is larger than that, because everything is at the maximum. So I changed a little bit the maximum, the exposure time, so we collect for less time. So here it's in live mode, so we are keeping on recording, like as if I was recording a video. And this is the beam waste of my beam. This is without the cylindrical lens. This is just because I have the objective. So I could also move in the other direction, so I could tilt in the other way, but you won't notice too much. Okay, the reason is that it will be this type of movement. We will notice more the effect when we will have the light sheet. Okay, so here, let's go back to the first mirror. We said this is a translation, this is very obvious, just rigid translation. What happens if I move in the other direction? So not up and down, but in the other one. I mentioned this, also, but also something else. Those are stripes due to the fact that there must be centers of absorption here. And they are casting a shadow behind, because I'm illuminating from the side. Okay? So now I'm going to move through the sample. Look, so what I'm doing, I'm moving the sample in this direction. Okay? So That's the surface, okay? That's the start of the gel. And then I can go inside, plane by plane. These are plane of fluorescence, as you can see. All these stripes are just due to center of absorption that are casting shadows behind.
It's like 3D scanning, right?
Exactly, it's like as if I was doing a 3D scan. So this is more or less the idea. So now I'm going to, who wants to align the system? I want 2 people that want to touch here the things. I'm going to misalign everything and you have 10 minutes. How much? No, 10 minutes. 5 minutes. 5 minutes. 1, 2 people. 1? Who else? You 2. Okay, I'm going to misalign everything now, okay?